Hello, welcome to some amazing physics. This is acceleration part 1, also chapter 3 part 1. All right, so we're going to be looking at acceleration. Acceleration, actually the best way to describe acceleration is that when you're moving, you feel it. So if acceleration happens, like for example, you're in your car, and I just want to let you know that I have superior drawing skills. And so this is a car. Oh, is that ever a car? And there you are. See that? You're smiling. And so if you're in your car and you're moving at a constant rate, you're not really going to feel it. And so if all of a sudden you speed up and this car surges forward, you feel it. If this car turns, you feel it. If it turns that way, you feel it. If it slows down, you feel it. So accelerations are a change in velocity, and you feel it. It's actually defined as, and it's a vector quantity, and so I kind of sort of talked about this right here. A vector quantity means that it includes direction. So anytime your velocity changes, because it's vector, that means if you turn, you're changing your velocity, and so that's an acceleration change. So it's defined at the rate at which an object changes velocity. And so rate is going to be, it's going to be something like this. It's going to be, acceleration is going to be a change in velocity divided by a change in time. So this is how you get that rate. All right, so let's look at a couple of examples here. So if you're riding on the roller coaster, why is it fun? Well, because there's a lot of accelerations. And there's accelerations because it's constantly changing direction, it's speeding up, it's slowing down, and those accelerations, we feel it, and it causes our stomach to drop out of our whatever, just lifts us up and drops us down and changes our whatever, and so it's a whole lot of fun. But if you're riding on an escalator, you're just going to go up that at a constant velocity, and it's not going to change. It's not going to be very much fun unless that thing all of a sudden sped up, slowed down, backed up. In that case, it might not be that much fun because it'd throw you off of it. But another good example of this is just the whole idea of the Earth, because we're on the Earth right now. Here's the Earth. There's some continents right there. There's you right there. Way there you are. And so you're on the Earth, and the Earth is constantly spinning at about 1,000 miles per hour, but you don't feel it. Why? Because it's a uniform velocity. There's no acceleration going on as the Earth spins around. And if there was some kind of acceleration, you'd feel it, and the results would be catastrophic. All right, so let's look at a couple of motion diagrams here, or particle models. So as you can see, the runners right here are closer together, and with each increment of time, and each of these increments of time is the same amount of time. So all these are going to be 1 second. So each space in between one of these is a second. And so you'll see within the first second, this person didn't go very far, but as we continued on, they continued to go further and further apart in the same amount of time, which means they accelerated. They essentially went faster. If you look at this one right here, you're going to notice that they're further apart in the first increment of time, and then at the end they're closer. So this person's slowing down. So this would be an example of a negative acceleration, and this is going to be an example here of positive acceleration. So you can speed up, you can slow down, you can change direction. All right, so here we are. Acceleration is termed as change in velocity divided by time. And so let's take a look right here at this graph and just sort of analyze some of these different accelerations. So you can see here, as we look at this first blue line right here, this is just called acceleration. And you can see that the velocity continues to increase. Now, to actually find the value of acceleration, all you'd have to do is pick 2 points and do a simple rise over run calculation. And so essentially, the acceleration equals the rise over the run, or as we say in math, that equals the slope of a velocity time graph. So if you have a velocity time graph, the acceleration is always the slope of that. So now you'll notice right here in this little bit of time right here, there was no change in acceleration. So my change in acceleration was 0 divided by time, meaning there was no acceleration. And so there's no slope, and that should help you to see that there's no acceleration. So if you have a velocity time graph and your velocity stays constant over time, then you have no acceleration. You'll notice in this next one, it's called deceleration. You could also call it negative acceleration. The change is negative. So you see you have a negative slope here, and you could calculate that negative slope if you wanted to add that out, and that would give you your acceleration negative. Now this particular graph right here, what's this showing? Well, this is showing a steadily changing acceleration. It's an increasing acceleration, but it's not a constant. So right here, the acceleration is just a little bit, and as we go over here, all of a sudden we get accelerating faster and faster and faster and faster. This is the kind of thing that a a roller coaster would do. It'd go like slow over this one point, and then speed up really fast. So what they want to do is change the acceleration. So this is showing a non-constant acceleration, a non-uniform acceleration, kind of like a roller coaster. All right. One last thing, though, if you're just to draw out accelerations pictorially, you would draw them as velocity vectors changing size. Here we are. Remember, each one of these dots is the same amount increment of time. So let's say that there's 1 second in between each of these. If we wanted to solve the acceleration from a particle model like this, you'd simply pick two vectors, two consecutive vectors. So I think right here, what we've done is we've picked two consecutive vectors. So it looks like they've picked this one, and they've called this one, I'm going to have to figure out how to quit doing that for you, V2, right? So that's velocity 2, or final velocity. And then this is velocity 1. Well, the change in velocity is going to be defined as the final velocity, or in this case, V2 minus V1. So the final velocity minus the initial velocity over the change in time. So if we look at this right here, we're going to take V2 and subtract V1 from it. So to subtract vectors, all you have to do is flip them the opposite direction. So that's what they've done here, you see. They've taken this vector. You can see there's the V1 vector, and they've flipped it the opposite direction. Now, the remaining amount, which is right here, the remaining amount of that vector is actually the acceleration. So this is the change. So when you take these two consecutive vectors, lay them up against each other, it'll actually give you the change. And so that's your acceleration vector. These are velocity vectors. Final and initial is your acceleration vector. So this one you're clearly speeding up. This one you're slowing down. As you see, they're getting closer together. So, so here we'll do the same thing. So our velocity 2, it looks like they chose, it appears they chose these two right here. So here's our velocity 2, and it looks like this is our velocity 1. So they took the velocity 2, they flipped the velocity 1, subtracted from it, and here is your remaining vector. And it is, of course, this is what's remaining, so it's in that direction. And so that one shows you that we have a negative acceleration vector going that way. And what about this one? Well, this one, you're going in the negative direction to begin with. So if you resolve two vectors, you would see that acceleration is increasing in the negative direction by this much. Looks like it's the same as the first one. All these look like they're about the same amount of acceleration. So this one, you're actually slowing down in the negative direction. So, so we put those two velocity vectors together, and we get a vector going in the positive direction, because any acceleration vector that slows you down is going to be opposite to your direction. And that should make sense. So you want to accelerate negatively, that's going to slow you down. Accelerate positively is going to speed you up. So this one, it's a little bit confusing maybe because we're already going in the negative direction. But that's a quick little run through of what is accelerations, what are velocity vectors, what are acceleration vectors, and what is an acceleration. So it's simply a change in velocity over a change in time. And the best way to understand it is you can feel it. All right. In the next one, we'll be doing some problems.